Hey everyone, and welcome. Today we're diving into one of the most elegant and powerful ideas in all of physics, gauge theory. It's the framework that forms the very backbone of the Standard Model, and it answers a question so fundamental you've probably never even thought to ask it.
And that question is, why are there forces at all? It's a surprisingly deep question. For a long time, physicists had this zoo of brilliant but totally separate theories for the interactions they saw. It was a list of rules without a reason, and there was no single underlying principle for why these forces should even exist in the first place.
And here are the usual suspects: electromagnetism, the weak and strong nuclear forces, and of course gravity. Each one was described by its own unique set of equations. Now, it worked, don't get me wrong, but it wasn't elegant. It felt more like a jumble of random laws than one coherent description of reality. Physicists knew there had to be something deeper, a unifying principle behind it all.
Okay, let's get into it, because this is the aha moment. The answer came from a profound idea that has been physics' North Star for over a century: symmetry. But we're not talking about just any old kind of symmetry. Gauge theory demands a very specific and incredibly powerful kind, known as local symmetry.
To really get this, let's look at the difference. A global symmetry is pretty simple. It's like saying, let's rotate the entire universe by 30 degrees all at once. It's rigid, one rule for everywhere. But a local symmetry, whoa, that's way more demanding. It says, I should be able to apply a different rotation right here and a completely different one way over there, and the laws of physics must still hold true. This seems impossible, right? I mean, how can the universe possibly maintain consistency if you're changing the rules everywhere, totally independently?
Well, here's the mind-bending solution. For the laws of physics to not completely fall apart under all those independent local changes, something must exist to communicate the changes from one point to the next. Think of it like a network of messengers, constantly telling each point in space how its neighbor has changed just to make sure everything stays consistent and in sync. The universe is literally forced to introduce this connection field to maintain order. And that new, necessary field, well, that's what we perceive as a fundamental force. Forces aren't just there, they are a mathematical necessity born from this intense demand for local symmetry.
And there's an official name for that golden rule: gauge invariance. The word gauge here is just a fancy term for a measuring stick or a local reference point. So gauge invariance is simply the principle that the laws of physics can't depend on how we set up our measuring stick at any given point. The laws have to be rock solid, completely invariant, even under all these local tweaks. It's this one powerful requirement that dictates the existence and nature of interactions in our universe.
So, with this incredible new key in hand, physicists began a century-long journey to unlock the universe's code, applying this principle of gauge invariance to understand the forces one by one.
Now, this idea didn't just appear overnight. It actually started, without anyone realizing it, with Maxwell's equations for electricity and magnetism way back in 1864. It wasn't until 1928 that Hermann Weyl formally laid out the gauge principle. But the major breakthrough, the real game changer, came in 1954 from Yang and Mills, who generalized the idea to much more complex symmetries. That work became the foundation that allowed physicists in the 1970s to build the Standard Model, unifying 3 of the 4 fundamental forces under this single, beautiful umbrella of gauge theory.
And this brings us to the grand result of all that work: the Standard Model of particle physics. I mean, this is arguably the most successful scientific theory in all of human history. And just look at the elegant structure that pops out. Each fundamental force corresponds to a specific kind of local symmetry, each with its own mathematical flavor and complexity. You've got electromagnetism, carried by the photon, arising from the simplest kind of symmetry. The weak force, the one behind radioactive decay, mediated by the W and Z bosons, that comes from a slightly more complex symmetry. And the strong force, binding protons and neutrons together with gluons, is governed by the most complex symmetry of the 3. It's an incredibly organized and beautiful picture where different forces are just manifestations of different types of symmetry.
And the power of this approach is just undeniable. It didn't just describe what we already knew, it made absolutely stunning predictions. Gauge theory led to the unification of the electromagnetic and weak forces. It gave us quantum chromodynamics, or QCD, our ironclad theory of the strong force. And, get this, it predicted the existence and even the properties of the W and Z bosons years before they were finally discovered at CERN. That's a serious predictive punch.
But for all its triumphs, the standard model isn't the final word. Its limits aren't failures, not at all. Instead, they're like giant signposts pointing us toward the next great frontiers of physics.
And the most glaring omission, the real elephant in the room, is gravity. Now, Einstein's general relativity describes gravity beautifully on the large scale, but it isn't a quantum gauge theory like the others. Fully incorporating gravity into this framework remains one of the single greatest unsolved problems in all of science.
And then there are the cosmic mysteries. Our current gauge theories have absolutely nothing to say about the nature of dark matter, the invisible stuff holding galaxies together, or dark energy, that mysterious force causing the expansion of the universe to accelerate. Together, they make up 95% of the universe, and we're, well, pretty much in the dark. Beyond those cosmic questions, there are other really deep internal puzzles. For instance, why do some force particles, which our theories say should be massless, behave as if they have mass? That's a huge mystery called the mass gap problem. Another is the hierarchy problem. Why is the Higgs boson, the particle that gives other particles their mass, so surprisingly lightweight compared to what our theories predict? And then, of course, there's the ultimate dream. Can we find a single, even larger symmetry that unifies all these forces into one grand unified theory? These are the puzzles that are driving physicists today.
So the crucial point to take away from all of this is a profound shift in perspective. Gauge theory teaches us that forces aren't arbitrary add-ons to the universe. They are a necessary consequence of its deepest, most elegant principles. The universe demands local symmetry, and in meeting that demand, the forces that shape our reality just spring into existence. Makes you wonder, what other secrets might be waiting for us, hidden within the language of symmetry?